Okay, so let's get started. So last lecture, we started talking about infinite sets and how to count the number of elements or how to compare the sizes of infinite sets. Okay, so we went over the concept of countably infinite, which basically means that you can list all of the elements of the list of the set in some order, right? Even though there are a number of elements, you can list them in such order such that eventually every element is going to be appearing on that list. Okay, and then we went over some examples, some properties of countable sets. So one of the things that we said is that if so for instance, it never works. So we said that if A and B are countable, then A union B is going to be countable, A intersection is going to be countable, and A cross B is going to be countable. And based on that, we were able to say things like the set of rational numbers is countable because it can be thought of as you know, the product of natural numbers with itself, and therefore you can count. And because we have this property that it's closed under the product operation, therefore we can conclude that the set of rational numbers can be enumerated. And we went through a particular order of enumerating products. So let me stop here for a second and see if there are any questions. So this is one of the sort of unfamiliar or really new topics that we are covering. So it takes a little bit of time to get a clearer picture of how all of this works. So we want to take the time to understand these concepts in depth, which means that so that's why it's good for people to ask more questions. And so let's see more cameras turned on. Okay. Courtney.
What would something that's not countable look like?
So we will get to that soon. So yeah, that's a very good question, because what you will find is that most of the things that we can think of, most sets we can think of, it seems that they are countable, right? And we will, show today that real numbers, the set of real numbers, is not countable. Okay. Joseph.
Oh, I just had a question. So, can you like give like a recap of what was countable so far? Because like I was working on the homework and like that was like completely like other topics, so like my memory is kind of a little bit blurry from Tuesday.
Okay, no problem. Let's do a very quick run through, right? So that's, I think, a reasonable. Let's see. So we started by refreshing ourselves on what are these surjective and injective concepts, which are definitely the things that you are going to be working on in your homework, right? And then we said how we can use these notion of like A surjects B, which says that somehow A has, uh, as many or more elements than B, right? And we are going to use that as a way to count, because if A surjects B, then we can say that A has at least as many elements as B, right? And similarly, if A injects B, then we can say that B has at least as many elements as A, okay? And if there is a bijection, which again, remember, think of it as a matching, right? So you find matched pairs between the two sets, and you make sure that everybody is matched. So then that's what a bijection is. And when you have that kind of a pairing, then you can see that the number of elements in the two sets should be the same. So and then we looked through this example again for how to use bijections to do the counting, and then we entered this this new concept, introduce a new concept of counting infinite sets instead of just saying, hey, it's infinite. Well, we want to say something more, okay? And then the very first question is, what is infinity, right? So we need some way of formally understanding infinity as opposed to having an intuition, right? Because the intuition is generally not that good, right? Because obviously the intuition is going to say natural numbers are infinite, and the set of real numbers is infinite, and everything else that seems to. So again, we can't tell. We can't rely on our intuition to tell us too much about infinity, because our intuition is good only for the things that we normally encounter on a if we have some familiarity with the concept in the real world, then our intuition is going to serve us there. If not, well, it's not going to really work. So again, less than half of the class has turned on their camera, right? So I really want, when we are doing these types of online classes, it's the only way to get some feedback is by looking at your faces, because it's difficult to talk. So Joseph, do you still have a question, or you just forgot?
Oh, I just left my hand on by accident.
Yeah, that's okay, no problem. So the infinite sets, it should be obvious that infinite sets have this property that if you add one more element, you can't tell the difference, right? That's intuitively what this is saying, okay? But the converse is also true, which means that if you cannot tell the difference, then then you can say that it is an infinite set. So right, so we have this property that if you have a bijection between A and A with the new element added, then that is exactly the definition of infinite. Okay, so this is a sort of formal definition, because once again, with infinite sets, many things that we normally do doesn't really work, because there are just infinite number of elements to get through, right? But it's easy, or it makes sense to talk about pairings between elements, and then say every element is paired. Now it doesn't matter whether there is a finite number of such pairings or infinite number of such pairings, as long as the elements are paired and every element has a unique pair, then the two sets must have the same number of elements, right? So that kind of reasoning we can accept, even if we are never going to be able to sort of go through and verify one by one whether the pairs exist or not. If the pairs exist and everything is paired, then we can definitely say the two elements have the same, two sets have the same number of elements. Okay, so and then we started talking about countable sets, which are either finite or countably infinite, right? And countably infinite means that you can list them in some order, right? So you can list the elements in an order such that every element will eventually show up. Okay, so again, always keep in mind that you need to be able to say that any given element will definitely appear in that sequence after a finite number of elements, right? Saying that it'll appear after an infinite number of elements is not saying anything at all. Okay, so what you need to be able to do is to enumerate the set in such a way that any given element that you are interested in will appear after a finite number of other elements. Okay, so this is the key point that you have to keep in mind. So, and it is also the kind of mistake that people tend to make when trying to prove that something is, countable or enumerable, as it's called, right? So you need to really say, is it going to appear after a finite number of steps? Okay, then it's countable. Okay, so we talked about the strategy for proving that some set is countable. One is, of course, the strategy derived from the definition. You simply produce an ordering in which that satisfies the definition of countability. Okay, and the second thing we are going to do is we are going to we can also rely blindly on these closure properties and then say, if I can construct a given set, okay, suppose you are asked to prove that some set X is countably infinite, right? If you can start from known countably infinite sets like N, Z, Q, and so on, right? So again, remember, natural numbers, integers, rational numbers. If you can start from these and then say that X equals, some expression involving these known numbers that is uses only these operations, then by the closure properties of these operations, you know that X is also countably infinite. Okay, but let's look at so there is a little bit of a difference between union and intersection here, right? Because we know that the union of two infinite sets is infinite, right? But what about the intersection of two infinite sets? What can we say, Greg?
We can say that it must also be countably infinite, since the intersection of two sets must be smaller than either of the sets.
Can you repeat your answer, because I think I missed part of it.
When you have two countably infinite sets and you take the intersection of them, the intersection must still be countably infinite because
correct. So that is what this closure rules are saying, right?
Right.
So
and
I'm asking you if you can say something more.
And that's because the intersection of two sets will be smaller than
right. But
either.
you're still saying, giving the justification for why they are closed under intersection, right? So the question I asked you is that the union of two infinite sets is infinite.
Right.
I asked you, what can you say about the intersection of two infinite sets? Okay. So now you answered a slightly different question, which is, what can you say about the intersection of two countable sets? And you said the intersection of two countable sets is countable, right?
Yeah.
It's not exactly the same thing as what is the what can you say about the intersection of two infinite sets?
My bad. I think I think I forgot the possibility that it can turn out to be an either infinite or finite set, but I think you still have the possibility of the intersection being an infinite or a finite countable set.
Yeah, so that's what I was asking. So although so we know for sure that if you take the union of two infinite sets, you definitely have an infinite set at the end. But if you take the intersection of two infinite sets, you can't say much about the size of the resulting set. The resulting set could be empty, right? Or it could be finite, or it could be infinite, right? So in that sense, intersection is different. Whereas if you take union and the cross product operations, then if you start with infinite sets, the result will definitely be an infinite set. Okay. So the second strategy for proving countability is that used to use these closure properties so that you can say, for instance, what we did was we said, hey, Q is, there is a bijection between Q and, Z cross Z, and therefore Q is countably infinite, right? Something like this is what we tried to say in the last lecture, okay? Okay, so I have a feeling that it's fine. And we went through another example of complex rational numbers, right? So let's call this the set X, and it can be, again, because P is an element of Q, and Q is also an element of Q, right? So these complex rational numbers can be described as a pair P comma Q, right? Which means that the set that we are trying to describe is essentially Q times Q, right? The cross product of Q and Q. And once again, using the closure properties, we can say, since this is Q is countable, Q cross Q is countable, and therefore the set of complex rational numbers is going to be countable, right? So what that tells you is that by doing simple operations on countably infinite sets, you are not going to go beyond countably infinite, right? So this is, I guess, was the question at the beginning of the class. How do we, go from countably infinite to some set that is larger? Okay, so that's the topic we briefly touched upon at the end of the last lecture, and something that we are going to spend most of today's lecture on. Okay, so let's take this example, the set of all finite length strings or a finite alphabet. Okay, so when I say finite alphabet, right, generally it shouldn't matter whether the alphabet has 2 elements or 20,000 elements, right? Because from if all you care about is finiteness, what's the difference between 2 and 20,000, right? So there's nothing, which means that when we think about a problem, if it doesn't matter whether the set has 2 elements or 20,000 elements, then we might as well work with 2 elements, because that's going to simplify our thought process, right? So whenever I say finite alphabet, you can always think with alphabet size equal to 2. Okay, many times alphabet size equal to 1, may not work, but so you should not go with 1, because if you think about strings drawn from an alphabet of size 1, then there is this unintuitive property that there is exactly one string of each size, right? Whereas if you think about alphabet that has at least 2 characters, then the number of strings of a given length, there is more than one, right? And then the number increases with the length, right? So if the alphabet is A comma B, and I have a string whose length equals n, okay? How many such strings of length n can I construct from an alphabet of 2 characters, right? So what that means is that I can construct, like if I take 2 length 2, then this will be going to be A, AB, BA, and BB, right? So if based on this, what can you say if the size or the length of the string is n, how many such strings are there? Joel.
2 to the n.
Can you just speak a little bit louder?
2 to the n.
Yeah. Okay. So and what about the size of the alphabet is k? Then how many strings of length n are there? If somebody else wants to try this? So we said if the alphabet is of size 2, the answer was that there are 2 to the power n elements.
It's k
yeah, go ahead.
K to the n, right? Or k to the k or whatever. Because
no.
No?
Which is it?
We're talking about
length
2
is
or k.
n, right?
Length is n.
And
The alphabet is k. I see. Okay, I get it now. Then it's k to the n, right?
Right. That's
Okay.
good.
I thought you meant the ICA.
Yeah, right. I just wanted you to, think for one more second, right? Okay. So what is a set? What does it mean for a set to be closed? Well, it's not a set that is closed. We talk about sets being closed under an operation, which means that you perform an operation and the result is going to belong to the set, okay? So this is sort of the technical definition of a closed, but if you try to understand what I said about closure properties, technically it's a little bit more complex than, it's worth understanding that way. So what closed here means is that if you start with 2 countably infinite sets, the result after applying these operations will also be countably infinite, right? So that's what we mean when we say countably infinite sets are closed under a certain operation, means that you take 2 countably infinite sets, apply these operation, and the result will still be a countably infinite set. Okay, so this aside, let's let me erase this because this is not really. Why do I have this trouble? Oh, okay, it refuses to erase, so maybe that's okay. Suppose I want to. What can we say about the set of all finite length strings over a finite alphabet? And again, as I said, well, finite, it doesn't matter whether it is just 2. So if it helps the thought process, you can just say, alphabet is only 2 characters. So what do you think? Is this countably infinite or not? Brian.
Well, we said it has a size, right? So it wouldn't be infinite, right? So
No, I asked you a side question about the size, the number of strings of a certain size. So I want to make sure that there is no confusion between that side question and
Oh, okay.
the problem here, which says all finite length strings. So if we can certainly ask that question, right? So how many, instead of saying finite length, if I said how many strings of length less than 1,000,000 exist, then what would be the answer? Alexander, did you have an answer? Do you want to answer that question?
No, I was thinking of the question before that. Can you restate the question you just asked again?
Yeah. If you are limiting yourself to strings of length 1,000,000 or less, right?
Right.
And the alphabet is finite. What can you say about that set? The set of all strings of a length 1,000,000 or less over a finite alphabet.
Oh, I mean, definitely countable, right? Because you can start with strings of length 1, followed by all strings of length 2, followed by all strings of
But
length
can you
3,
say
right?
more than countable?
Infinitely count? I'm not sure what.
No, it is finite, right?
Right, yes.
Okay, so that's
Oh, yeah, fine, yes.
right. So when we say countably infinite, that includes both finite sets and infinite sets.
Right.
And so we want to always give the sort of more, informative answer, right? Which,
All right.
so if something is finite, we want to say it's finite, and then if it's, so right. So again, it doesn't matter that it is 1,000,000 or 1,000,000,000,000 or 10 to the power 100,000, right? It doesn't really matter. Finite is finite, right? So now let's get back to the question which maybe you wanted to answer. Why don't you answer? You said that you wanted to answer the original question. Do you want to try that now?
I think I'll just leave that to someone else for now.
Okay. Good. Anybody else? At this point, you either have an idea or you can guess. I'm looking for more people to, stick their neck out, especially when I say it's a guess. More people should be able to, guess, right?
The question is infinitely countable.
What can you say about this set? That is the question, right?
Yeah.
So this example is given. Is that finite? Is that countably infinite? Or is it more than countably infinite?
Isn't it just finite? Because it's not an infinite set. So to be countably infinite, it has to be infinite and countable, but it's not infinite, right?
Okay. Okay. So let's go here, right? So that's a good answer. Let's go to the next page where we make a small change. Okay. So there is definitely a catch here, which is that no, there is no catch. I'm sorry. Yeah. So let's get back to this one. Okay. So the set of all finite length strings over a countably infinite alphabet. So once again, so sometimes when somebody says something is finite length, it's a bit unclear exactly what it means. A better term to use is bounded length. Okay. Because when you say something is of a bounded length, that means there exists some number such that everything is smaller than that bound. Okay. So if I tell you that all of these strings have a length less than some constant, the constant could be astronomically large. But if I tell you that there is a maximum bound, then it's much easier to see that this is finite. If I just said finite length strings, it's not entirely clear what it means. Okay, but this one, let's look at it. It's a slight variant where instead of saying finite alphabet, we said infinite alphabet. Okay. So once again, the answer here is that this is simply a finite set. Okay. And again, what I wanted to do was change it to bounded length. Okay. So here we have a slight difference, which is that the alphabet is infinite. Okay. So what can we say in this case? Somebody wants to take a guess? Well, there are, okay, so let's see. I want more new people. Let's see. Joel.
Hello, you hear me?
Yeah,
It's infinite.
it's infinite. And is it countably infinite, or what can you say?
Countably infinite.
Okay, so do you want to argue why it is countably infinite and not just-
Actually,
yeah.
It's not countably infinite. I don't
Okay.
think so, at least.
Okay, by which you are saying that you cannot think of a way to enumerate them all.
Yeah.
Good. Anybody else wants to try if there is a way to enumerate it in such a way that every string that I want to find will eventually be there? So again, notice that this is a countably infinite alphabet, right? So if I said uncountably infinite alphabet, of course, the answer is very clear, right? Because if I have an uncountably infinite alphabet, then I can't even, list strings of length 1. So this is a countably infinite alphabet. So does anybody want to try Joseph?
So the goal of this is to like pair every single string with like a member of that infinite alphabet. Is that like the goal?
No. You're just enumerating the strings in that in that, right, over that alphabet.
Okay.
So you want to enumerate these strings in such a way that every possible string will eventually appear in this ordering, in this list.
Okay.
Brian.
So I think you could start from strings of length 1 and then go up. And for strings of greater than length 1, you could think of it as the sets cross each other. So I think it should be countable for like 1, 2, 3, and then you can just keep going to be as large as it wants. So I think it would be countable.
Okay, so you start with string of length 1, and then what do you do?
So for a string of length 1, it's just going to be each character of the alphabet, and that is countably infinite. And then for a string of length 2, it's like one.
No, but how are you going to list these strings of length 1?
Well, a string of length 1 would just be one letter of the alphabet.
There are infinitely many of them, right?
Oh yeah, yeah.
So
So
again,
it's not.
this is some kind of a scheduling problem, right? So if you do all the length 1 strings first and then get to the length 2 strings, right?
Oh yeah.
Like the problem that we did last lecture, then you'll never get to length 2 strings.
Yeah.
But we already know how to avoid getting stuck that way, right?
Yeah.
Okay, so how do we do that? Anybody else wants to try? Oh, okay, I'm sorry, I should have noticed. Michelle?
Like, wouldn't it be countable because like we can start with like length 1 and then you put like a couple of letters and then go to like strings with 2 letters.
I,
And, like,
I,
kinda
I'm
have,
having
like,
a little bit of
pattern.
a hard time understanding you. Can you speak up a little bit, or maybe just try again? So this time maybe I'll hear you.
Can you hear me now?
Yeah.
Okay. So like we can like make a pattern, like start with string 1 and then like put a couple of letters
Mhm.
and then like go to like strings of 2 and then like have a pattern and then keep going down like strings of 3, strings of 4 to show
Right. So
that
for
like
instance, we could say, I'm going to, one string of, length 1, right? And then, sorry. Okay, so again, the idea is that you don't get stuck listing all of the elements, strings of length 1. Instead, you're going to keep switching between strings of different lengths, right? So you can, for instance, do one string of length 1, right? And then you can go and then do one of, length 2, right? And then you could come back and do another one of length 1, then you do another of length 2, then another of length 3, and so on, right? So think of it this way. So can you enumerate strings of length 1? Okay. So if I ask you, instead of saying I'm sorry. So instead of just saying finite length, if I said string of length 1 over an infinite alphabet, you can immediately give me an enumeration, right? Because you just have to enumerate the alphabet. Okay. Now, if I ask you for string of length 2, then that is, like sigma cross sigma, right? Because it's a sequence of length 2. So that's like a product. So we already know how to list a set, the elements of a product in such a way that every element of the product will show up. So this way we can say, there is an enumeration of all strings of length 1. Here is an enumeration of all strings of length 2. And here is enumeration of, all strings of length 3 and so on, right? And then we can use the same visual thing that we did, which is we list that, we output that element, then we go down, we output this, then we output that, then we come back here, then we output all these 3 elements, then we come back here, and so on. Okay, so the point is that you do these kinds of constructions in steps, right? So first you say, L2, right, which consists of all strings of length 2, is enumerable, right? And you can prove that. And then you can prove that L3 is enumerable in the same way, and L4 is enumerable in the same way. So once things are enumerable, then you can write out the infinite sequence somehow, right? Of course, you'll never finish writing the sequence, but there exists this infinite sequence. And once all of these sequences exist, then you can, do your zigzag pattern through the sequence in such a way that, and that zigzag pattern you can see is going to get to every string eventually. Right? Does it make sense? So this kind of zigzag pattern and sort of switching between different types of elements in order to make sure that everything eventually appears in the enumeration, right? So that's something that we do again and again. to prove that something is countably infinite. So far, we have been talking about, countably infinite. And of course, the question is, what is not countably infinite? Okay. So in order to address that, we need to have some formal way of saying that, what it means for things to not have the same size, or for one set to be strictly larger. Okay. So once again, we are going to use the notion of surjection for this purpose. And we are going to say that A is strictly larger than B. Okay. I'm sorry, not A is strictly smaller than B. Okay, so that's what it says. So strict means so A is strictly smaller than B if, essentially the way to read that is that if there is no way to cover B with arrows from A, right? So A surjects B. Once again, if you remember, recall that surjects means that every element of B has an arrow coming in, right? And because when we say A surjects B, we are talking about functions. So any incoming arrow will have some element of A attached to it on the other side, right? So which means that if every element has if every element of B has an arrow coming in, then there must be corresponding at least one element on A, which basically says, well, A has enough elements to cover all of B, right? So that's what A surjects B means. Not of A surjects B means there is no way to do that, right? Again, A surjects B says that there is some way, right? Some relation from A to B that covers, or some function from A to B that covers all of the elements in B. When you say not of that, that means that there is no way to map the elements from A to B in such a way that all of the elements of B are covered, which means that somehow, there should not be, somehow the only way that can happen is that if A simply does not have the necessary number of elements in order to cover B, because we are allowing any function, right? So we are not saying, okay, the function has to be such and such. We are allowing any function, which means that any element of A could be paired up with any element of B. And when you say A does not surject B, that means there is no way to pair them up in such a way that all of the elements in B will be covered by the elements in A, which seems to be the definition of what it means for A to have fewer elements. So that's how strict, strictly smaller is defined in the case of infinite sets. Okay, and of course, when we think about it in the context of a finite set, of course it makes sense, right? So if A has strictly fewer elements than B, then there is no way to put arrows from A to B such that there is at most one arrow coming out of every element in A, right? And once again, you have to get that in, internalize that a function means that there is, and at most one arrow coming out of the elements in A, right? So when we say A surjects B, we say that there is a function from A to B that covers every element in B. Okay, so for finite sets, we clearly know that we can't cover a set B with, say, 10 elements using a set with just 9 elements, because, well, if you try to pair, then at most 9 elements on the right can be covered using the 9 elements on the left, right? So therefore, in a finite case, of course, it makes sense. In the infinite case, again, we sort of accept it as the definition of when one set is strictly larger than another. Okay, so finally, we come across the first theorem that says something about sets that could be larger. Okay, and what it says is that the power set is always strictly larger in size than the set you start with. Okay, so this was a theorem proved about 150 years ago by Cantor. And it's a very, very interesting theorem because until then, mathematicians used to think that it's a frivolous exercise to think about infinity, that it is sort of a meaningless entity, and nothing good will come of a mathematician's career if they spend the time or waste their time thinking about infinity. And so when Cantor started working on this, so everybody sort of dismissed him off, saying, he's out of his mind. But eventually he found a way to prove that power sets are strictly larger. And so, for instance, if you take the set of natural numbers and then you construct the power set of natural numbers, right? So subsets of natural numbers and count the number of such subsets, that is strictly larger, right? So we can say that right? So the size of the power set of natural numbers is strictly larger than the size of natural numbers. So let's see how we go about, proving. And this is a little bit, sudden. So far, it was all about constructing some order, right? So that somehow seems intuitive, right? So we can, we have some way, some pattern, some some technique for enumerating things in a certain order. But now, how do you show that there is no such order, right? Because we can think of an order, but how do you say that nobody can think of any order because it's impossible, right? So this is sort of difficult. Okay, so I'm going to ask you again for more of you to, turn on your cameras. Okay, so I'm not going to continue until I see enough people on my screen. How about that? Okay, good. So so this is where Cantor was stuck for many, many years, right? Trying to figure out how to prove that there can be no such mapping, and ultimately, he figured out. Okay, and this is the proof we started looking at the end of last lecture. So unlike the examples we saw before, right, where the alphabet may have been infinite, but the strings were, not necessarily infinite. But here you have all infinite strings, right? Okay, so now what happens if you have infinite strings? So for infinite strings, Cantor was able to give an example that shows that essentially constructs an infinite string that is different from every element in this enumeration, right? So the way this proof works is it is a proof by contradiction, right? So you tell me that you claim that this list of infinite strings over 0, 1 is countably infinite. So since you say that, I ask you to produce a listing, right? So you produce a listing, okay? And then I give you a proof that regardless of the list you gave, right? My proof works and it shows that your list is not complete, okay? That is, there is a string that is never going to show up in the list you produce, okay? So this is how I'm going to be able to prove that no matter how you list your string, right? No matter what order you choose, the order is not going to work. The way I'm going to prove that is by constructing an example that regardless of the order that you produce, that counterexample is going to be a string that's not in that listing, okay? So how do you do that? There is a fairly simple strategy, and that strategy is that you give me this string. So I say, hey, tell me the first character of the first string, okay? So you say it's 0, okay, I'm going to, make my string start with 1, okay? So now I know that this string cannot be the first string you listed, okay? So then I ask you, what is your second string? Okay, so you tell me second string. And I ask, what is the second position of the second string, okay? So you tell me it's 1, okay? Then I say, okay, I'm going to make my string 0, okay? So now I know it's not going to match the first 2 strings, okay? And then what is the third digit of the third string? 0, okay, I'm going to make it 1. And fourth digit of the fourth string, okay, so essentially I'm going to flip one character of each string that you give me, okay? And that character that I flip is kind of like a witness that tells me that the string I'm constructing is not going to match a particular element in this enumeration, right? So this is a witness against S1, right? It proves that this cannot match S1. So this is a witness against S2. This position is a witness against S3 and so on, right? And because it's an infinite string, right? So because this is an infinite string, the more number of elements that you give me, I produce, more digits in the string to show that it cannot be that element, right? And you can keep listing forever, and I can keep producing digits here. And therefore, this string that I'm going to give you has not appeared. And no matter how long you keep listing, the string that I produce would never be there, right? Does it make sense? Okay, so this is called diagonalization because, well, what you're doing is that if you think of this as a matrix, then this is some kind of a diagonal you're going through, right? And then you are reading off the diagonal and you're flipping the bits, right? So your counterexample is you take the diagonal and then you flip it, and that's really your the counterexample, right? So that's why the term diagonalization came about. In a more general context, diagonalization really doesn't involve constructing diagonals, but this visual example is actually very, very helpful to understand how the proof works. And so the name diagonalization came from this, visual representation of how this proof goes, and it gets stuck there. Okay.
Professor, just a quick question.
Yeah.
Back here, what is the order in which like S1 and S2 and S3 are generated?
We don't know, right? This is sort of an adversarial argument, right? Somebody claims they can list them, right?
Right.
And I say, no matter how you list them, here is a way I can construct a string that's not going to be in that listing, right? See, that is the genius of the proof, right? Because if you know how to, list it, then you can prove that, okay, that listing doesn't work, right?
All right.
That's easy enough.
Yeah.
But the problem is, how do you prove that no listing will work, right?
Okay. I understand. Yeah.
Right. So that's why this proof took, people years and years, and obviously why lesser mortals won't be able to come up with a proof like this.
Of course.
Right. So it's not something that, well, it's a mathematician of the century that will think of an idea like this, right? But once the idea is discovered, then we get good at applying it, and even all of us can see how to apply the idea in other contexts. Once we see a few more examples, we will be able to do that, right? But to come up with the idea for the first time is just mind-boggling. Okay, so so this is about a particular problem, right? So uncountability of infinite strings. Okay, now this certainly is sort of one way of proving that, at least more or less proving that real numbers are uncountably infinite, right? So because this proof says that infinite strings over 0, 1 are uncountable, right? Now you can interpret an infinite string as a real number, right? So think of it as a, let's just think of real numbers between, in the interval, 0, right? Real numbers between 0 and 1, right? Excluding 1 itself. So we can sort of interpret each of these as, with a binary point, right, before that. So this you can think of, point 1, 0, right, is in binary is 0.5 in decimal, right? So if you're not entirely familiar with that, then you can sort of think about it offline. But essentially, just like any sequence of decimal digits after a decimal point is going to be able to represent some real value in this range, right? Similarly, you can produce a binary string to represent a real value in that range, right? And you can show that each such fraction, right? So you can just say 0.11, 10, 11, whatever, and how many other digits you list, it is still a number, right? It's still a natural, still a real number. Therefore, there is one real number corresponding to each of these, right? And therefore, if this set is uncountably infinite, you can say that the list of real numbers between 0 and 1, that is also uncountably many. Okay, so there is a way to go from here to real numbers, and in fact, that's how that's why this proof came about, right? Not because people were thinking about just infinite strings, but they were thinking about infinite strings as a way to represent, arbitrary real numbers. Any other questions? So your next assignment, right? So you're thinking, I haven't even started on the current homework, and we are talking about the next one. Well, yeah. So the next one will be handed out, when you hand in this, the current homework, and the next one will be, the topic will be just these, countably and infinite and uncountably infinite. This will be the topic, and yeah, so you will need to be able to show that some sets are countable, some sets are uncountable, and so on. Okay, so so it makes sense to again stop me and ask questions if you're not following anything that we have discussed so far. Okay. At the same time, do keep in mind that these are all really new topics, and so it's natural for it to take some time to understand these concepts and be able to internalize them, right? So this is why I kind of go over the material multiple times. So right, so I very quickly went through this proof at the end of the last lecture, and it's almost the end of the next lecture, and we are still on the exactly same proof. So I will definitely go through this material slower than what we have done with the more straightforward stuff that we went through in the last few lectures. But but you do need to stop me and ask questions. Okay, so again, when you have yeah, so when you have a question, make sure that you don't just put it on the chat. You try to lift your hands. And Courtney, do you have a question? I'm sorry. Sometimes again, I may not notice, and you should just unmute and ask your question, right? I find it hard to be keeping an eye on the all of the panels when I'm talking, because my CPU is at 100%. Okay, so yeah, go ahead.
Going back to the slide where it was the finite length strings over a countably infinite alphabet.
Mm-hmm.
So what we said was that you would do like length 1, then length 2, then length 1, 2, 3, and yeah. I was just confused on how you would know when to do strings of length 2 if the set of length 1 strings is infinite.
Yeah, so this is the picture, right?
Yeah.
So we already know that strings of length 1 are countably infinite. So we list them like this, right? So here, right? So we produce this, right? So this listing exists, right?
Mm-hmm.
Similarly, for length 2, this list exists, right?
Mm-hmm.
And list 3, this list exists. So that means that these elements that I circled, we already know what they are, right? And therefore we can just go through them in this order, right?
Oh, okay. So it's like,
once again, you don't have to quite know. You just have to say, hey, because it's countable, because each of these sets, L1, L2, L3, L4 is countable, I know that there exists some order in which the elements can be listed. Then once I know that the order exists, I don't have to know exactly what element is there. I should just, I only need to say how to switch between them in such a way that every element, right, no matter how far to the right you're talking about, right, and how far down you are talking about, right?
Mm-hmm.
So I should be able to get to that element, right? And this zigzag strategy will get you to any element, no matter how far down or how far to the right it appears.
Yeah,
right?
so you're zigzagging between only one element.
Yeah, when you
Okay.
zigzag, each zig, lists, one element each from each of these sets, right? And
Yeah.
then when you zag, you just come back to the beginning.
Okay.
Right? When you zag, you are not doing anything. And then when you zig, then once again, you do one element from each set. Yes.
Okay, thank you.
Okay. Is there any other question? Okay, so let's see. So now we want to give sort of the more general proof that power sets are always bigger than sets. Okay, so the idea is going to be, somewhat similar to the proof that we just saw. Okay, so we want to prove that power set of n is uncountable, right? And we are going to use the same strategy. You claim that P of n, power set of n, is countable. So I ask you, okay, then list the sets in some order. Okay, so what you're going to do is you're going to say, hey, here is my first element in my enumeration. I'm going to call that, S1. Second one, S2. Okay. Now, what I'm going to do, right, is that I'm going to construct a set that will never appear in this sequence, right? So this is the same strategy that I'm using from the previous proof here, right? So if somebody can list them, then I tell you a way to manufacture a new string that is not equal to any of them, right? So the same way I'm going to manufacture a set that is not going to be equal to any of them, okay? So the way I'm going to do that, roughly speaking, is that I'm going to take this set S1, okay? And I'm going to find, intuitively, you can think of it this way, right? So if I want to take this strategy and translate it over here, then what I might try to do is, if you give me S1, I take one element that's not in S1, and I say that's in the counterexample set S that I'm going to produce. I'm going to pick one element that's not in S1. Okay. Then you give me S2, then I take another element that's in S2 but not in. So then I pick another element that's not in S2, and I add that to my S, right? So I keep doing that, okay? Which means that now I have constructed a set that is not equal to any of these elements, right? So that is the basic strategy. So construct S by drawing at least one element, okay, that is not included in SI, right? And each of SI is, of course, finite, right? Because if you keep listing, correct? So you obviously couldn't be listing anything that's infinite, right? If you are going to produce elements any element you produce has to be finite, right? Because there's no way of producing anything infinite unless you have infinite amount of time to produce it, right? So anything that actually gets listed in this sequence has to be finite, okay? So there is a difference between this problem and this problem, because when you think about the problem here, we have already said we are talking about infinite strings over 0, 1, right? Whereas here we are talking about subsets of natural numbers, right? So and these subsets, right? So need not be so these subsets need not be finite, right? So again, that's not a requirement. It need not be finite, but even if they are infinite, unless they are equal to the set of natural numbers, which is sort of a special case, let's not consider that, right? So then you'll always be able to find some element that's not in there, and you can use that as a witness to construct this set S that's not going to be equal to any of the elements that have been listed so far, and therefore you have a contradiction, and so the implication of that contradiction, right, which applies to this proof as well as this proof over here, is that you claimed that you could produce this list, this set in some order. I have proved that you are not able to, right? So therefore, it must be the case that the set is not countable, right? That's why you could not enumerate it in some order in such a way that every element will appear, right? So because I have told you there's an element that's never going to appear, and I have proved that to you, that means that there is no way for you to list this set in an order that satisfies the definition of countably infinite, okay? And therefore, this set must not be countably infinite, okay? So that's why this set of infinite strings over 0, 1 is not countable, and that's also the reason why this set, which is the set of subsets of natural numbers, is not countable, okay? So what I will do now is that I'll try to prove something slightly more general, right? Because this is somehow, based on the set of natural numbers, right? So let's try to prove something A strict power set of A without necessarily making any assumption about what A is, okay? And we can no longer count on rely on somebody being able to enumerate the elements, because we don't know whether A itself is countably infinite or not, right? It could be uncountably infinite, right? So we could be talking about A being the set of real numbers, right? And we are saying that the power set of real numbers is still larger than the set of real numbers, right? So we can't really use enumeration, so we need a slightly more general way to think about it. And what we are going to do is we are going to think in terms of surjections, okay? And so what we are going to do is we are going to go back to this definition, right? So A is strictly smaller than B if we can show that there is no surjection from A to B, okay? So what we are going to do is we are going to use the same idea from the diagonalization proof to prove that there exists no surjection from A to the power set of A. Okay, so this is what we are going to do. So how do we do that? And that's okay. So the way we do this is we want to show that there exists no surjection, right? So what we are going to do is that you are going to claim, right? Here is the surjection, okay? And I'm going to give you an example, right? So again, so this is A, and this is the power set of A, okay? And you are going to claim that there is a surjection that you have produced, okay? And what I'm going to do is I'm going to construct an example that is not there in the surjection that you claim to provide, okay? So that's what, I'm going to do, okay? So given where we are, I think I'll just stop here because, I cannot possibly complete the proof at this point, okay? So, once we complete that proof, then, then we are pretty much done with this chapter, okay? Because this chapter is about relations and size of infinite sets. And once we prove that the power set operation allows you to construct, larger and larger sets, right? Essentially. So you can go from set of natural numbers to the power set of natural numbers, and that will turn out to be the same as real numbers, okay? And then you can go from real numbers to power set of real numbers, and power set of that, and power set of that, and so on. And that's a way to create an unending chain of larger and larger infinities, right? So that's the and at that point we'll sort of say okay, and then move on to the next topic. Okay. So any questions? Okay. Okay, so enjoy 2 minutes off at the end of this lecture, right? So we always ended right on time. So this is the first time we're ending like 2 minutes early. Okay, again, I'll stay here if anybody has questions, but feel free to hang up.
Thank you.
Thank you.
Just a quick one, Professor.
Yeah.
So can you go back to the diagram where A surjects B?
This is long ago.
No, it was you had just made it to prove that, oh, here's, you say.
Is this the one?
Well, okay, not this one, but the point was like, you have to show that the surjection that they made, that, know, they have this surjection, but you show, no, that's not true. You're missing this point or something, right?
Yeah.
But aren't there infinite mappings you can make between A and B?
Correct, of course. So that's why it is difficult to so you have to have a particular way of constructing this element that's not covered. In fact, what you do in the proof is that you don't construct just an element. You kind of think about the element and the arrow together, and then what you're going to say is that so you have to think about that together in order to complete the proof.
All right, thank you, Professor.
Not a question about the class, but for a test, I asked this on Piazza a little while ago.
Yeah.
Would I be able to use a valid high school ID for like
yeah, as I
if we just
said,
respond to
we will figure something out, right? So
yeah,
I guess, you know, if you are on campus, then of course you will have, you know, your campus ID.
yeah, but
and you won't have an
unfortunately,
issue. But
yeah.
if you are not here, then we have to, you know, and then again, many of you will have driver's licenses, and then that works. But obviously, some of you are not going to have, you know, either of those. Then we'll just work with whatever you have.
Great, thank you.
Yeah. Okay. Bye.